Today we're going to move on to section 10.6, and like the last couple sections, we'll have all the notes today with a short assignment, and then tomorrow you'll have more problems to do in the section. This section is about finding segment lengths in circles. So just first of all, a quick reminder from some of the work from last week. Last week was all about the measures of arcs and angles. So in this problem over here, we're trying to find the values of A, B, C, and D. And when we look at these, we're given the measure of this central angle, 108, so we know that the measure of the central angle is equal to the measure of its intercepted arc. We're given the measure of the arc over here, that's 156. We don't know C, which is the remainder of the circle. So to find C, since the whole circle is 360, I would subtract those other two arcs, and I would get that C is 96 degrees. Now we have all the arcs, and we can start looking at the angles. Angle A is formed by a tangent and a chord. And an angle formed by a tangent and a chord is equal to 1/2 the measure of its intercepted arc. So the intersected arc goes from this point of tangency around to where the chord hits the circle. So A would be 1/2 of 96, which is 48. B is another angle formed by a tangent and a chord. So it would be 1/2 of its intercepted arc, which goes all the way around here. 1/2 of 156 is 78 degrees. And then we have a couple ways we could find D. We could take 180 minus the 78 and the 48 to add up to this straight angle. We could also know that D is 1/2 of its intercepted arc because D is an inscribed angle. So D would be 1/2 of 108, which is 54. Over here, we have an angle X that is an angle outside of a circle where two secants intersect. So the rule is that that angle is 1/2 the difference of the intercepted arcs. 1/2 of 70, that would be 35 degrees. I'm going to put up a summary from the chapter that has all the rules for the arc and angle relationships, as well as the relationships from today's notes. So today, we're going to look at what happens when we have different segments that intersect inside or outside the circle and how those lengths are related to each other. First, a quick definition. When two chords intersect in the interior of the circle, like here, each chord is divided into two segments that are called the segments of the chord. So R and S are segments of this chord, T and U are segments of that chord. And there's a theorem relating those lengths. It says, if two chords intersect in the interior of the circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. The product of the lengths of the segments of one chord, R times S, is equal to the product of the lengths of the other chord. R times S is equal to T times U. When we talk about a secant is defined as a line that intersects the circle in 2 points. A secant segment is a segment that contains a chord of a circle and has exactly one endpoint outside the circle. So here in this picture, AC is a secant segment. The part of the secant segment that is outside the circle here is called the external segment of that secant segment. So here I have secant segment AC with its external segment AB. And we have a rule about secant segments that intersect. If two secant segments share the same endpoint outside of a circle, so here I have AC and AE that have the same endpoint outside the circle at A, then the product of the lengths of one secant segment and its external segment equals the product of the lengths of the other secant segment and its external segment. Let's break that down with this diagram. The product of the lengths of one secant segment, so AC is a secant segment, and I want the product of that and its external segment, which is AB, equals the product of the lengths of the other secant segment. The other secant segment is AE, and its external segment, AD. You have to be careful with these. It is the entire secant times the external part. AC times AB equals AE times AD. All of these theorems can be proven using similar triangles. We probably will not see those proofs, but that's where this relationship comes from, similar triangles and then sides being in proportion. One more rule. When you have a secant segment and a tangent segment. If a secant segment and a tangent segment, so here's my secant segment AD and my tangent segment AB. So the tangent segment has its endpoints at the point of tangency and then out here at A. If they share an endpoint outside of a circle, point A, then the product of the lengths of the secant segment and its external segment equals the square of the length of the tangent segment. The same relationship we had on the other page, I have the entire secant times its external segment, AD times AC, is equal to the square of the length of the tangent segment. Basically, kind of think of this as the tangent only has an external segment, so it's the whole thing times the external segment, which is AB times itself. Now we'll look at some examples using these properties. Here we want to solve for x, and this is two chords that intersect inside of a circle. And the rule is when two chords intersect inside the circle, the product of the segments of one chord is equal to the product of the segments of the other chord. 6 times 4 equals 3 times x. So that's 24 equals 3x. Divide both sides by 3. I get x equals 8. Over here, same idea. We have two chords intersecting inside the circle. The product of the two segments of one chord, 4 times 3, equals the product of the two segments of the other chord. So I have 12 equals 8x minus x squared. Here I'm going to move everything to make one side equal to 0, and I'm going to move it so that the x squared term becomes positive. Add the x squared over, subtract the 8x, and the 12 is still there. That equals 0. This factors. I need factors of 12 that add up to negative 8, which are negative 2 and negative 6. And so that gives me two answers. And if I look at these two answers in the diagram, if I substitute in 2, then 8 minus 2, this side of the chord would be 6, and this side would be 2. If I substitute in the 6, 8 minus 6 is 2, and then this side is 6. So these two answers are both valid, and what they are the two numbers that split the chord into segments that are 8 and are 2 and 6. We just don't know which side is longer, so there's no way of knowing that it's one of those as opposed to the other. In this diagram, we have two secant segments intersecting a point outside the circle. And this 8 and 12 is the length of the entire secant segment. The rule is that it's the secant segment, the whole thing, times its external segment equals the secant segment times its external segment. 8x equals 48. In this case, my x is 6. Down here, I'm given the parts of those secant segments, so I need to make sure that the first thing I do is look at how long the entire secant segment would be. This secant segment is 6 plus x. Down here, 5 plus 7, this whole secant segment is 12. So I have the secant segment times its external segment. 6 times 6 plus x equals 5 times 12. External part times entire thing equals external part times entire thing. And multiply this out. Subtract the 36 from both sides and divide by 6 to get x equals 4. In this picture, I have a tangent segment on one side and a secant segment on the other. Its secant segment times its external segment, the whole thing is 9, the external part is x, equals the tangent segment squared. Divide 36 by 9, and I get x equals 4. Down here, I have the tangent tangent squared equals, I need the entire secant segment. X plus 4x is a total of 5x. So it's the secant segment times its external segment. This is 20 squared is 400 equals 5x squared. I need to divide both sides by 5 first, which gives me 80 equals x squared. And then I'm going to take the square root of both sides. In this case, x is a length, so that x has to be positive. So x is the square root of 80. 80 is 16 times 5, so this is 4 square root of 5. We like those exact answers where we don't have to round. One last problem, there's a little bit of an application here that we can do. We have an arch that supports a pipeline across a river 20 meters wide. Midway, the suspending cable is 5 meters long. So we have a pipeline going across the river that's 20 meters long. Midway, there's a suspending cable that goes up to an arch. That arch is part of an arc, excuse my drawing, and so it's part of a circle. That's pretty poor drawing. So this suspending cable is 5 meters long. The whole pipeline was 20 meters, which means it's 10 meters on each side. What we need to do is find the radius of the arch, which is the distance from the center of the circle that contains that arc to the edge of the circle. There's a couple different ways that you can do this problem. One way is to draw in a radius here, add in the rest of this cable coming down, which has to be perpendicular because it comes to the midpoint. And then if the radius is r, this piece would be r minus 5. And you can do Pythagorean theorem with this right triangle. And that's a way we could have done this problem earlier in the chapter when we talked about chords. Now we have an alternate method. Here's my circle. I have my pipeline with my cable. So this is 5, 10, and 10. And what I'm going to do is, again, I know that this is going through the midpoint. So when I extend it, it's going to go straight through the center of the circle. So what I'm going to do is I'm going to use the property from this section to find this whole length. 5 times x equals 10 times 10. 5x is 100, so x is 20. That's this portion of this diameter. So if I add the 5 to it, I get that the diameter has to be 25, which means my radius is half of that 12.5 meters. So we can piece together how to find those missing pieces. One comment on this section, again, if you feel like you don't have enough information, extend the lengths of some of your segments, draw in a radius to an important point. Those can all be ways to get more information.